Okay, the topic this hour is going to be the so-called real gas law. And what this means is that real gases, which all gases are, actually behave somewhat differently than the ideal gas law itself. And this was observed by measurement by various people as one went to higher pressures and lower temperatures and observed how pressure, volume, and temperature change for gases. And so we're going to look at this, basically the deviation of the pressure, volume, temperature behavior of real systems. And systems, we mean when those systems are behaving as a gas, whatever that might be. And its deviation from the so-called ideal gas law behavior. All right. So what was done is that you basically go out and make measurements, and the quantity, pressure times volume divided by the number of moles, the gas constant, and temperature. This quantity was, in a sense, tracked for real systems. Now, they might only be changing one thing at a time, like pressure at a fixed temperature. They'd fill a container, some kind of a cell that they can control. They could control the volume of the cell. Yes.
The thing that with gas is there's several different types of gas.
Right.
Like, and they have different molecular structure, but yet they all seem to follow the same relationship with the compressibility factor. Like,
Yeah.
does their size and shape not really alter or affect it all that much?
Yeah, we're going to get there. He's talking about the similarity that different gases behave with respect to, at least in some ways, they behave in a similar way. We'll talk about how they behave similarly. Okay. So this term here should equal 1 for an ideal gas, and so they basically just made a definition of this term and said that anything that's not 1 would be a deviation. It could be less than 1 or greater than 1. And we want to track how that deviation goes as a function of, for example, pressure and or temperature. So we go out and make some measurements.
Excuse me?
Uh-huh.
This deviation doesn't mean that the gas is not ideal, yeah? Because at very high pressure,
Uh-huh.
very high pressures, it's maybe become 1.
That's right.
Yeah.
That's right. The value, the numerical value of Z, is by definition 1, of course, for ideal gas. But for a non-ideal gas or a real gas, its Z factor at some particular pressure and temperature might also be 1, though it's not behaving ideally. Okay. It's kind of a cancellation of errors or cancellation of deviations. Deviations caused by pressure and temperature. Okay. So the pressure's pulling it one way and the temperature's pulling it the other way, and the total net deviation is 0. So the ratio, this deviation factor is 1. So we're going to make some measurements, and let's just say that we set up an experiment where we, for example, have 200 degrees, and then we make a series of measurements of volume. for a fixed amount of moles. Okay, this might go from 1 to 100 or 1,000 or whatever bar, and we basically make measurements of the volume. Okay, and then we take that and calculate from. So these are the measurements, and then we translate all that into this term Z. And then we change the temperature of the system. Maybe we make it cooler, and we do the same thing. Or maybe 100 bar, 200, 500 bar, however high pressure you can take yourself. Fairly simple experiments because it's just a container. You have to know its volume. And what happens when you take, and people actually did this kind of measurement and plotted this Z factor here versus pressure. For example, if we use open symbols for the first set of data, then what they saw is that this went below 1 initially, and then it kind of turned the corner and started going greater than 1. And then actually at some pressure out here, it actually reached the value of 1 again. But then it kept getting larger and larger, and it continuously got larger ad infinitum, actually. And then let's say that I'm just going to make it, even though I know it should be triangle next, that's what I say in the notes. We go to a lower temperature and we do the same thing. And once again, at 1 bar, which is close, very low pressure, the Z factor is close to 1. And then this thing goes further down. Doesn't quite hit the minimum at the same point. And then something like that. Okay, so they all these at least down to a certain temperature have this kind of behavior. But then if you went to some real high temperature, maybe like 400 degrees C or something, and you actually might see that this thing just and it goes like this. It goes higher, something like that. Most petroleum systems in the reservoir, at reservoir temperatures, have this decreasing to increasing type behavior. Very few reservoirs are high enough temperature to actually see this monotonically increasing deviation. Okay, so this is at typical reservoir temperatures. And I've told you that's around 30 C to 200 C plus. And your point made earlier that even though the value of Z is equal to 1 here, this is definitely non-ideal. In other words, the molecules themselves are not behaving as ideal molecules. Okay, and the point where they reach this value will be different for each gas. Okay? Now, not only do we have a fixed number of moles here, but we also had a fixed compound or gas component. For example, methane. Okay? Now the compounds that, in a sense, by themselves are gases at reservoir conditions would be methane, nitrogen, CO2, H2S sometimes, normally, and perhaps C2 as pure compounds. Okay? Or if you have a lot of that compound, any of these, it could have lots of other heavy stuff, but it would still behave like a gas. Okay? So reservoir gases basically consist of reservoir gases consist of, and I'm just going to say, large quantities of these 5 components. Okay? You could have hundreds, maybe thousands of other heavier components also, but these would be the dominant components. Large, whatever you want. And there was a guy back in the late 1800s, of course we have to go get a picture, by the name, a Dutch fella, by the name of Van der Waals, who around 1870 something or another, he was describing the behavior of not only gases but liquids and gases and liquids and things that you didn't know if it was a gas or a liquid. And he was describing the state basically in terms of pressure, volume, and temperature. And he was looking at both gases and liquids and don't know fluids. Don't know if it's a gas or a liquid. Okay? And he came up with this concept, or they call it a theory, which I don't understand, really, of corresponding states. The theory of corresponding states. And it's kind of like all mixtures or all compounds behave in the same way. Okay? In terms of pressure, volume, and temperature, if the variables are not actually pressure, volume, and temperature, but there's some kind of dimensionless pressure, volume, and temperature. And each gas has to have a special value of pressure, volume, and temperature with which you calculate this new variable. So basically introduce what's called reduced variables, which were reduced pressure, defined as the actual pressure divided by some special, as I'm going to call it a critical pressure. We'll learn more about that a little bit later, probably next week. And this is the absolute temperature divided by the critical temperature. And you also have the reduced volume, which is just the volume divided by the critical volume. Okay. Well, in a sense, what he said is that if any two, and I'm just going to talk about gases now, but it also applied to liquids, but I'm just going to say if any two gases, since we're talking about gases, have the same value of PR and TR. Okay? Then they will have the same reduced volume. Okay, but we're not going to deal with reduced volumes in this course. For gases, they will basically have the same Z value of deviation from ideal gas law. So you'll observe the same deviation from ideal gas if you have methane or ethane, assuming that they're at a pressure and temperature where these are the same. These reduced variables are the same. And what that means is that this deviation of gas behavior is only a function of reduced pressure and temperature. We normally write it this way. Okay? And it doesn't matter which gas you're talking about, if it's methane, ethane, nitrogen, or whatever. Okay. And PC and TC, these are the critical properties. And so what is a critical property? This is getting a little bit ahead of the course flow, but the critical properties, the easiest, this gets a little bit complicated, but every compound has a critical pressure and temperature. Mercury, methane, H2O. Okay, what is it though? Okay, I'm just going to try to give you a very quick. If we take something like water, which you're familiar with, okay, and we plot pressure versus temperature, and we go down here to 1 atmosphere and 100 degrees C, okay, what is that? What is special about that? It is where the water starts to boil, right? Cup of coffee in the morning, you have to go there to get your coffee, okay? So it is a condition where the H2O is what we call saturated. Okay, it can either be a saturated liquid, the boiling in your kettle, or if you just keep boiling it and you put a balloon on the end of the kettle, right? And a balloon without much stretch, it'll stretch without much force. So that balloon will just get bigger and bigger and bigger, right? Until it's about when that last drop of water from your liter of water that's boiling, when that last drop of water boils off into steam, that balloon is going to be about 1,000 liters, 1 cubic meter. Okay? But the water itself is just as happy to be a molecule in the steam, in the balloon, or in the kettle as liquid water. It has exactly the same chemical energy. So the molecules of water just don't care if they're in the steam or in the water. And that's called a saturation condition. Okay? So the difference, though, between the steam density, which is 1 kilogram per cubic meter, and the water density that you're putting into your cup is 1,000 kilograms per cubic meter. That's a huge difference in the physical property of density, right? If we redo that same experiment, at 300 degrees C, okay, then we're going to have to bring this pressure way up to get the same condition of that liquid water being gas or liquid, okay? But the point is that if we look at the ratio of density of liquid to density of its vapor, water over steam, okay? Here, it was 1,000. Here, it'll be maybe only 10. The steam will be much more like the liquid water. Its density will be much higher because it's at a higher pressure and a higher temperature. And what happens is that you get this entire locus of these things. Okay? And if we go to this temperature, the ratio of density of the liquid to the vapor is only 2. So that vapor is starting to look more and more liquid-like. And in fact, the liquid's getting lighter and lighter. And this thing will just kind of keep moving its way up until it reaches a point here where the contrast is 1.01. That density of the liquid is just almost, the density of the liquid and vapor are almost the same. And this point here, where they become equal, the steam and the liquid and the vapor become the same physical property of density, viscosity, whatever. That's the critical point. And it happens for mercury, it happens for benzene, it happens for any compound. And I plotted it on a linear scale, but that's because this is on a log, and this is 1/T. I mean, but there's a line, there's a continuous line. And this is called the vapor pressure line. Okay? The vapor pressure line. And the end of that line, the end of the line, is the critical point. That's the critical point. Each compound has a single pressure temperature. Okay. So we know that for all the compounds. And what van der Waals said is that if you take your pressure and divide it by the critical pressure and the temperature divided by the critical temperature, that substance, if it's a gas, if it's behaving like a gas, it will have the same Z deviation from ideal gas as any other substance if it is at the same TR and PR. That's what this corresponding states theory says. Well, this is way back in the 1870s. And there were measurements coming along into the 1800s, through the 1800s, and then in the 1900s. And around during the war, in the 1940s, in the petroleum industry, there was this Professor Katz, Donald Katz, at the University of Michigan. He got his first PhD student, whose name was Marshall B. Standing, who was the first professor, one of the very first professors at this department. After he retired from a long career, he basically gave him the task of collecting all of the existing Z-factor data for all gases and measuring more Z-factors for natural gases. Okay? That was his PhD work. And then to meticulously take all of that data, which was supposed to behave the same, according to van der Waals, and to plot it up into a meticulously plotted set of curves. That, as of today, the curves are more accurate than any equation that tries to describe them. The guy was just phenomenal. He used something called a French curve and a lot of... So they took and they developed a generalized set of Z-factor charts, which were a function of not just for ideal compounds, but for mixtures of gas and so forth. Okay? And it's called the Standing-Katz Z-factor charts. Okay? So they took all existing data, plus new data for petroleum mixtures. And I'll show you that that chart here. I hope. Okay. So this is the chart. Okay. And you can see that it's kind of plotted in a funky way here. Along the x-axis at the top, it goes from 0 to 8. Okay. And then the Z factor starts at 1 at low pressures, at 0 pressure. It starts at 1. You can see it dropping down. And most reservoir temperature, reduced temperatures are greater than 1.2, 1.3. So that they tend to drop down here. Only very high reservoir temperatures, you see it would be monotonically increasing. And what you can see is that these curves start crossing, and this is on the lower, this is an extension. This curve here is actually just an extension of the upper right here. Okay? So he's made two figures and kind of cut it into two pieces to fit it onto a chart like this. And so these the deviations, and you can see that it never reaches 2, and basically never will in any of the reservoirs. Somewhere between 0.7 and 2. But that's a lot of deviation for engineering. Remember your bank account. You know, what kind of deviation you allow there. Okay. So these are the charts, and for each one of these lines, it's got a constant temperature, reduced temperature. Okay. So that's so that chart was there. I'm just going to try to do something here. I'm going to, for the sake of having it on in the notes, I'll just make a little clip of it. And we'll dump it in here. Just so you'll have it in the notes here. Okay. All right. Kind of out of scale, but doesn't really matter. It's in there. Now, the other thing that's important, and you can tell that he was given the task of measuring new data for mixtures, is the question is, will this corresponding states theory work also for mixtures, not just single compounds? And the answer is yes. And in order to do that, for mixtures, simply need to come up with an average what we call pseudo, instead of average, calling it average, we call it a pseudo-critical pressure, which in general is just calculated as the molar average. This is mole fraction. Mole fraction. You know, 0.8 methane, 0.1 ethane, and so forth, times the critical temperatures of each component. And the pseudo-critical pressure is calculated in the same way. This is for all the components in the mixture. Like that. So it's this, you know, pseudo average pressure and temperature. So what you need is the mole fraction of the reservoir gas. This is the reservoir gas mole fraction. Both places. Let's get rid of this. There are lots of mole fractions. There's separator gases. There's all sorts of mole fractions out there, but it needs to be the reservoir gas mole fraction. So much methane, so much nitrogen, etc., etc. And if you have that composition and you have the individual component critical pressure and temperatures, then you can calculate this, call it average or pseudo value. And then you calculate the so-called average or pseudo-reduced temperature as the actual temperature over this pseudo-critical, and likewise this average pseudo-critical pressure. Typically this is ranging from about 1.3 to 2.5, and of course this can go from 0 to about 20 in extreme cases of high 1,000 bar like pressures. Now, these mixing rules for getting the averages, they have an asterisk, because if you have H2S, CO2, and if you have these heavy molecules, a significant amount of them, C7 and heavier, what we write C7 plus, then you have to do some special things. This requires special treatment. And you'll find this discussed in chapter 3 of the book. The special treatment with respect to these so-called sour gases, H2S and CO2, is a method by a guy named Wickert, who was a PhD student of Khalid Aziz at Stanford. And this is when they were up in University of Calgary in Canada. Corrects for the sour gases. And the C7 plus, Standing and Katz kind of took care of. What they showed is that the TC of the C7 plus material and the PC of the C7 plus material, that these were different functions. There was a function, and it basically depended on its molecular weight and its density of this heavy material. Some other function. So it would be different for different fluid systems, okay? So you need to know something about the C7 plus characterization. Was it more paraffinic or less paraffinic? They came up with they used a correlation by Matthews. It's in that book chapter, and they had this method to come up with estimates of the critical temperature and pressure for these heavy ends. But by hook or by crook, once you get these two numbers here, you can go into the Standing-Katz chart and find the deviation. Okay?
Excuse me.
Yeah.
7 plus is always going to be different, isn't it?
It'll always be different. So when you have the C7 plus, you have to have these two numbers for your C7 plus. If you have those two numbers, then this correlation by Matthews et al. Will give you estimates of the TC and PC for your C7 plus.
Okay, so we experimentally determine the...
That's right. These are lab measured. And they're different for each reservoir.
But is this only for gas?
Well,
Is this to determine the compressibility factor?
yeah, this will apply for anything that is behaving like a gas at reservoir conditions. Okay.
But the 7 plus, that's not going to be like a gas.
Well, but if you take 70 moles of methane and 10 moles of ethane, okay, and 5 moles of other light stuff, and you put a few moles of C7 plus in it, it'll still be a gas.
Okay.
It's like water. There's water in this air, right? Water is something that comes out over here at these conditions, right? Liquid. That liquid is absorbed into the air. It's in solution in the air, right? It's exactly the same. The C7 plus stuff gets absorbed into the reservoir gas.
But you need a lot of the other stuff, I think.
Exactly. That's exactly what you have. So, yeah. But when that stuff comes to surface conditions, it's like cooling this. If you cooled this down enough, you'd get the water drops coming out of the air, right? And you could analyze it. The water, of course, it always look alike. It's clean. It's always clean water in the air. Okay, but when it condenses out, the oil from the C7 plus stuff condenses out from the gas when you bring it down to low pressure and temperature. Then you can measure the molecular weight and density of that condensed C7 plus stuff. Okay.
And CO2 is different because of the structure.
That's right. The CO2 and the H2S, they're non-ideal. They're kind of like, they're doubly non-ideal. So there are special corrections, and those corrections depend on how much H2S you have and how much the other components you have and so forth. They're interactions of the H2S with the other components in a non-ideal way.
And the mixture average, you can incorporate the C7 plus into that?
That's right.
Okay.
That's right. That's all the way out to C7 plus or whatever, however far you want to go. Yeah.
Okay.
That's right. And I believe in Appendix A, Appendix B, you'll find example calculations of this. We'll be giving you also some, but example calculations. In fact, next hour, that's what we're going to be doing. Okay. Okay, so at the end of the day, what we end up with is our real gas equation, our real gas law, looking like this. Pressure times volume, moles, gas constant, temperature, nothing new, right? And then we've got the Z factor, which itself is a function of pressure in reduced form and temperature. Okay? And it could be a quite nonlinear function of pressure and temperature. And this is the Standing-Katz chart. There's also equations that fit the chart. And you'll find that in Chapter 3. Kind of pretty complicated equation, actually, that fits that chart. And just remember that the range typically is about 0.7 to 2, which is, that's a lot of deviation. I mean, even, 0.9 to 1.1, that's 10%. That's quite a bit. So let's see if we can find some pictures. What do you say? I don't know. Remember how to get images. It's a good looking picture. Not a very proper scaling. Okay, that's our my colleague, Professor Gualong, he'll probably show up one day sometime here. We're talking about these different people. He knows the history of all these people. I mean, you go in and read about them. I mean, I should say it. I should do it myself, but I do it and then I forget. But they're fascinating stories behind all these people. I mean, you know, they might be criminals for all you know. I mean, a lot of interesting stuff going on there. Certainly a lot of interesting hairdos. Let's see here. We've got Standing-Katz. See if we got him. I think this is him here. I met him once. Just gotta make sure. Donald. No, that looks like a doctor. Let's see. Standing-Katz. What would his University, S.A. Michigan. There he is. He's passed away some years back. I know. Where's all the girls going? Okay. And then he was not standing. He passed away just two years ago. Well, that's kind of unfortunate. Let's see. Marshall Standing. Let's see, maybe must. No. I can give it up yet. Most standing. It's kind of a shame. Doesn't look like we're going to make it here.
Will he be in Wikipedia?
Probably not. Unfortunately. I'll find him. I'll put it on there later. So, this is his professor, Standing-Katz. Okay, so these are the guys who kind of were helping us out on getting this stuff, and I'll get a picture during the break. What we'll do in the next session will be working an example of the using the real gas law.